PBS viewers. My name is Professor Brian Schmidt of the Australian National University. And this is part of the Great Minds series. And today we're going to be talking around the expanding universe, past, present, and future. Now, to understand the expanding universe, we really need to go back to the beginnings of cosmology. We talked around the development of general relativity, Einstein's theory of gravity. But that really wasn't developed for cosmology, although it ended up being used for it a lot. The first part of cosmology done by observational astronomers, people who go out and look at the sky, I think was done by a person you may not have heard of, Vesto Melvin Slipher. He was an astronomer in Arizona, USA, and he went out and spread the light of galaxies out into the colors of the rainbow, a spectrum. And when you do that for any object, you see areas of brightness where atoms emit particular colors, or these same colors absorbed, depending on exactly the physical conditions. These spectral lines allow us to very accurately identify, for example, what is in an object, for example, like the sun. So when Slipher looked at galaxies, he could tell that they were made up of many of the elements that we see here on Earth. But there was something different. Their light was shifted to the red, red-shifted, as we say. Now, Slipher knew that there was a way to shift the color of light, and it was through what we call the Doppler shift. Most of us are aware of the Doppler shift, for example, when we see a police car coming towards us, and the siren is pitched high. And as it goes by, the siren pitches low, and that pitch change is the Doppler shift. Things that come towards you, their frequency is raised for light. Light color is made bluer. And as they go past you, when they're going away from you, the light color is made redder or the pitch is lowered. And so Slipher realized when he looked at galaxies and they all had light shifted to the red, he realized that something was funny in the universe. We seem to be in a very specific point in the universe, a point where everything was moving away from us, kind of violating that notion of Copernicus, which we are not the center of things. And so this was a mystery when he made these observations in 1916. Now, the way we figured out what was going on was through another set of observations. Observations about how far away those galaxies are. So it turns out measuring distances in astronomy is really hard. You can't just lay a ruler down to the nearest star or galaxy. Rather, we have to look at how it appears. Now, it turns out that a candle or a light bulb, the further away it is, the fainter it appears. And this is something Newton figured out back in the 17th century. So we can actually go through and estimate objects' relative distance by how bright stars are in them if we can choose similar stars. And this is exactly what Edwin Hubble did. He had access to the biggest telescope in the world, the Hooker telescope, and he went out and looked at Slipher's galaxies and how bright the brightest stars in those galaxies were. And when he did that, and he estimated the distance, so the galaxies with the brighter stars were the closest, and the fainter stars the furthest, with the relationship, it turns out, as being an inverse square law, he was able to make a plot where he saw that the faster the galaxy was moving away by Slipher's measurement, that is the bigger the redshift, the fainter its stars. And this data was presented in 1929, and from it, he announced to the world that the universe was expanding. Now, why did he come up with that idea? Well, let's think of the universe as a cartoon. I want you to think of the universe as a bunch of galaxies spread around, and through the magic of our mind, we are going to expand the universe by a bit. And when I expand the universe and I layer before with after, what do I see in this thought experiment? I see that the nearby objects have moved a little bit. The distant objects have moved a lot. That is, the nearer an object, the slower it's moving away from us. The further the object, the faster it's moving away from us. In this thought experiment of an expanding universe, we see exactly what Hubble and Slipher observed. That the further an object is away, the faster it moves, the universe appears to be expanding. Now, Einstein's theory of gravity, developed by Einstein to understand, I think, an aesthetic nature of the universe, that gravity and acceleration are interchangeable, turns out was almost immediately used by De Sitter and others to go through and look at how the universe itself might behave. And as I said, his theory predicted that space will be curved, but it also allowed us to think about how the universe would behave in a way that Newton's laws could never be used. And that's because Newton's laws, when applied to a universe without end, provided only one solution that made sense, which is that the universe is empty. There couldn't be anything in the universe for it to make sense. And so as people started going through and playing with Einstein's equations, they realized that the solutions were dynamic. The universe had to be in motion. Now, when Einstein looked around, when he first realized this in 1917, he said, this can't be right. The universe is static. And so he added a fudge factor. That fudge factor he called the cosmological constant. And we can think of it as energy equally spread everywhere in the cosmos. This energy, it turns out, when you plug it into his equations, causes gravity to push rather than pull. And he thought by having the right amount of this in the universe, he could balance out the universe and make it static. Now it turns out this was a mistake. A butterfly on one side of the universe would cause the entire universe to start in motion. And so it was an unstable universe. And later he described this as behaving like a donkey, that he hung on to this theory for so long that the universe must have this energy spread throughout the cosmos. So Einstein's theory actually predicted that the universe should be in motion and might be expanding. But it was too big of a thought for Einstein to come to terms with. The likes of Alexander Friedman, who was in Russia, went through and actually calculated the trajectories for universe. And what he realized is that there were families of solutions to Einstein's theory of general relativity. And it depended on whether or not the universe was light, heavy, or just right. But one thing I want to point out is that Einstein's view of the universe was not so much that the objects, galaxies, are in motion away from us, but rather that space is being created between us. And that when we see a distant object, its light is shifted to the red because as light travels through the cosmos, it gets stretched by the expansion of space itself. And so when we look to a very distant object, we're looking into the past. The light takes a long time to reach us, and as it travels, its wavelength gets stretched by the expansion of space. So further, more stretching. Further back in time means further in distance. So these family of universes are easily thought about first by how we went through and we used the expansion of the universe to understand how old the universe is. So one of the things that Hubble realized is that he could go through and wind the universe back in time. Now, for whatever reason, people didn't think about the natural end. Well, most people didn't think about this. But if you take a universe that is in motion outward and you run it backwards in time, then you get to a time when things are closer and closer and closer and closer, and eventually you get to a time when everything is on top of everything else, the Big Bang. But we were able to think about running the universe back in time, and essentially if you run the universe forward, we see the universe expanding, but if we make a graph of how far away two galaxies are apart over time, we see that if we run the universe in backwards, we get to a time when those two galaxies are on top of each other. That's the time of the Big Bang. So if I measure how fast the universe is expanding now, I can run the universe in reverse and figure out how old the universe is. That is exactly what I did for my PhD thesis, which I finished under the supervision of Bob Kirshner at Harvard University in 1993. And what we discovered is that the expansion rate of the universe implied that the universe was about 14 billion years old. And that's something that the Hubble Space Telescope was used to measure very accurately, and we're continually making better and better measurements. And the answer is still to this day around 14 billion years. But we had to make an assumption back then that the universe was expanding at the same rate over time. That is, when we drew a graph, that the line backwards that we extrapolated was straight. But we know the universe is full of stuff. And we know that gravity will pull on the universe and slow it down over time. And so if we were to make that graph with a curved line, the universe might well be younger than we thought if the universe didn't have anything in it. And this has ramifications for the future. Because imagine a universe that's not slowing down, that does not have much stuff in it. It just gets bigger and bigger and bigger over time. It goes on forever. Whereas a universe that has stuff in it slowing down, if it has enough stuff in it, well, it will slow down to the point that it eventually stops and goes in reverse. It's like throwing a ball up in the air, have it going up and then coming back down to ground. So a universe that's heavy, that has a lot of stuff in it, that's a universe that starts with the Big Bang, but it ends in a Ganab-Gib, a Big Bang backwards. And it turns out that Einstein's theory of general relativity predicts all of this in almost perfect detail. And so the slowing down of the universe, if we can go out and measure it, affects how old we think the universe is from the Hubble constant. That is, Hubble's constant is how fast the universe is expanding now, but it also tells us the fate of the universe. If the universe is slowing down quickly, the universe will stop, go in reverse, and end in the future. If it's not slowing down quickly, then the universe continues to expand forever and is infinite into the future. But Einstein tells us that gravity curves space. And it turns out that a universe future trajectory is integrally related to how heavy it is. So a universe that is heavy means that gravity curves space onto itself. And this is a universe that bends literally in the fourth dimension onto itself. It's a universe, if I head out that direction and I have enough time, I could, in theory, eventually come back to where I started. A light universe, on the other hand, bends away from itself like a saddle. And so light, in this case, travels on curved hyperbolas, if you think about it within our four-dimensional universe mathematically. And finally, there is a perfect universe, one that is perfectly balanced between being heavy and light, the just right universe. That universe, space neither bends away from itself or onto itself. It's just right. It's flat. In this universe, triangles have 180 degrees, and everything goes on forever. And it is a universe that expands forever, but comes to rest in infinite time into the future. So those are the three possibilities for a universe full of atoms. And those three possibilities are what brought me to Australia in 1994. Because in 1994, I told the director of Mount Stromlo Observatory, where I am here, atop a mountain just outside the Australian capital, that I could look back into the past and measure what the universe did in the past, and thereby figure out the universe's future.